All right, welcome back. I think we're going to go over some calorimetry equations. So this term calorimetry, right here. So calorimetry, we'll talk about it but before we do that, we'll have to talk about heat. So heat, I'm going to drop down here, right? Heat is the total kinetic energy of a substance. So heat is symbolized by Q, right? So if we saw this, I kind of obstructed it a little bit. So heat is symbolized by the symbol Q, right? And Q is the representation of the total kinetic energy of a substance. Because if you think about things that are moving back and forth cause friction, and everything that has temperature has friction. So every molecule in your body is rubbing against another molecule in your body, and that gives you your body temperature. The blood flows through your vessels, and that kinetic energy of the blood scraping against your vessel walls produces friction, which produces heat, and that kinetic energy gives you temperature. So there's a couple of things that we have to talk about. So the first is specific heat, right? Specific heat is the amount of heat it takes to raise 1 gram of a substance 1 degree Celsius. So an example, in specific heat is symbolized by C, where heat is Q. Okay, so specific heat with the symbol C is the amount of heat it takes to raise 1 gram of a substance 1 degree Celsius. Right, so the specific heat of water is 4.184 joules per gram degree Celsius, or simply 1 calorie. All right, so these are things that you'll have to write down and remember because we'll use them over and over and over again. All right, so the heat of a substance is different. So if you think about us, right, we're all made of essentially the same stuff, right? So we all have the same specific heat because specific heat is based on what something's made out of. But all of us will have a different heat for different sizes. So if you're larger, you have more heat than someone who's smaller, right, because you have more mass. So heat, we'll say that heat depends on mass. For specific heat, depends on substance. So if I had 10 grams of gold and 10 grams of silver, right, they would have different heats because they're made of different stuff, because they both have different specific heats. If I have 10 grams of gold and 10 grams of gold, they would have the same heat because they have the same mass and the same specific heat. All right? So specific heat depends on substance, but remember the important part here of specific heat is to raise 1 gram 1 degree Celsius. Right, so for specific heat, it's really important. It's joules per gram degree Celsius. That's the formula for it. So if you get a specific heat question, you have to put it down. All right, so let me give you an example of heat. So the formula to figure out heat, so heat is Q, and this is the formula for figuring out Q. Right? Q is equal to M, and M here is mass. C, remember, and T is temperature in Celsius. Right, so when we did gas equations, we did Kelvin, but mostly in chemistry we use Celsius. If you get a C that's in Kelvin, you have to make it a Kelvin, but most C's are in Celsius. All right, so calorimetry. So calorimetry we use a lot. So calorimetry is a method for isolating, let me put it down here so you can read it, is a method for isolating the external environment so the energy of reaction can be calculated. So there's a thing called a bomb calorimeter, right? So this is a bomb calorimeter view here. So this is the reaction vessel. So that's where your chemical reaction takes place. So whatever you want to measure the heat of, you'll put down in that little cup down there, the sample cup. Now you have ignition wires, which will light it on fire. right, or star to give it that activation energy it needs to get going. I have a little stirrer here, right? The stirrer is a propeller that's going to spin around and circulate the water, and a thermometer to read what it is. So the way that this works, so the water represents the environment, right? So the reaction is there, and the water is the environment, and the outside of this bomb calorimeter is insulated so we don't lose any temperature. So the important part is right here. So Q of the water, so the heat of the water is negative Q of the reaction. So if this produces heat, that means my products are losing energy, then energy is being gained by the water. Okay, so let me shrink this down a little bit. All right. So as water heats up, energy is released from the vessel cup. Then heat is exothermic. So let me give you an example of it. All right. So if I take this, so a reaction of sulfuric acid was carried out in a calorimeter. The reaction caused a temperature of 27 grams of liquid water within the calorimeter to rise from 25 to 76 degrees Celsius. All right. So if I remember that Q equals mCT, so that's equal, so my mass is 27 right? And I know my change in temperature is my final minus my initial. So I've got 76 right? So my C, right? My C here was my specific heat. So if you remember, my specific heat was 4.14 joules per gram Celsius. So if you look at the way this is set up, my grams are going to cancel out. My Celsius is going to cancel out. And I'll be left with joules, and that's what I want. Right? So but I want joules. So my temperature here, 76 minus 25 will be what, 51? Right, it's for 51C, but I canceled out my Celsius, I remember. I think that was right. Yep, 51. So let me get my calculator out here. So I've got 27 times 4.184 times 51. So I get 5.76 times 10 to the 3 joules, right? Or you could say that it's 5.76 kilojoules. So that's my Q. Equals 5.76. Right? So my delta H is equal to negative 5. Right? Because remember, my Q of the water is equal negative Q of the reaction. So what this is saying is my products, my reactants lost this much heat. So my reactants lost this much heat, right, to transfer it to the water. That's what it means. Okay, so here's a different type of problem. So this problem is different because this one asks you to calculate the specific heat capacity. So when you see a problem like this, it's important to remember that C is equal to joules per gram degree Celsius. Right? So if you think about, if you know what the units are, then you can place things in it. So I've got a 15.75 gram piece of iron. It absorbs that many joules, right? And its temperature changes to that. Right, so let's go. So we'll say C is equal, right? My joules are going to go on top. Right, I got grams down here. So I've got 15.75 grams. And my change in temperature, right? This temperature changes from 25 to 175. So 170, so I have 150 degrees Celsius. So that's my final minus my initial. All right, so let's do that. Let me get my calculator out. You get yours out. And I get no, I only had 2 digits. Well, it won't clear. All right. I'm just going to go back. I should have 2 digits, but it won't let me erase it for some reason. All right. So, nope, it won't let me erase. All right. So I get 0.476 or 0.46 joules, which makes sense, right? All right. Okay, so here's one last equation to look at. Right, I got 4-gram sample of solid silver was heated from, so how much energy was involved, right? So this is just another simple Q is equal to mCt. So it's not in a calorimeter. Now it's actually for the Q of the solid gold. So again, we have a mass. C was given here, 0.129. And my change in temperature, let me see what that was. So this is 40K. So this is equal. So remember that each increase of 1 Celsius is equal to 1 increase of 1 K. So you could just simply say, my erasing does not work, that those are the same. So they're interchangeable. Right. So let's do my math here. I got 4 times 0.129 times 40 equals right? So I've got that many joules. Because remember, during this, my grams canceled out and my Celsius canceled out. Right? So I got that many. All right, well, I hope this was helpful and it'll help you on your homework, and I will talk to you very shortly about Hess's law.